Hi everyone, my name's Alex Jenkins and I'm a postdoc at the University of Cambridge, and I'm really pleased to be giving a talk as part of this Early Universe from Home online conference. So I'm going to be telling you today about a new way of trying to test the physics of the early universe using cold atom analog experiments. So these are quantum experiments that can be built in the laboratory on a tabletop. And I'm going to try to tell you about some ways in which these systems can tell us about the physics of vacuum decay or first order phase transitions in the early universe. And this is work that's been done with a great team of collaborators. But someone I'd like to highlight in particular is Emily Hertig, who's also giving a talk as part of this conference. So if you're interested in these topics, I'd really encourage you to go and listen to her talk as well. So the plan for the talk is I'm going to start by telling you about what vacuum decay is and why, as cosmologists, I think we should care about it. And then I'm going to tell you about how we can try to simulate this process in the laboratory using these analog experiments. And then to finish up, I'll tell you about some of the theoretical work that myself and my collaborators have been doing to bridge that gap between the experiment and the early universe. So it's a very simple picture that we are trying to capture here. So we have a single relativistic scalar field that obeys this Klein-Gordon equation, but this potential that the field lives in can be kind of arbitrarily complicated. And in particular, you could have situations where the field gets stuck in a local minimum of the potential, when really it wants to get down to the global minimum of the potential. So we call that global minimum the true vacuum because it really is the ground state of this system. But locally, if I just explore small deviations away from this local minimum, it looks like a vacuum state as well. So hence why it's called a false vacuum. And so, if I were to try to get down to the true vacuum, trying to take the entire field over or through the barrier or whatever would take a lot of energy. So typically what happens is that in a small kind of localized region of space, the field will transition to the true vacuum. And this region then looks like a bubble. So the bubble of true vacuum nucleates in the false vacuum and starts expanding because it then wants to convert more and more of the field to this lower energy true vacuum state. These bubbles nucleate, they expand, they collide with each other. It's quite a simple visual picture to think about, like in this little cartoon here. But the sort of quantitative details of this process are really complicated. It's a non-perturbative, non-equilibrium process in which quantum effects can be really important. So it's a really challenging problem to try to solve. So I'm now going to show you a 2D lattice simulation that kind of captures some of the physics I was just talking about. So we see this field is in blue in the false vacuum, and it's kind of seething with these little vacuum fluctuations. And then at some point, if I wait long enough, these bubbles of red, the true vacuum, start nucleating, expanding, colliding with each other. We get some kind of very complicated dynamics, and then we end up with the universe is essentially just filled up with the true vacuum. And these kinds of transitions, the kind of thing I've just shown you, can happen in all kinds of different settings in cosmology. So I want to emphasize this is a really kind of generic physical process that can play a role in inflation, baryogenesis, gravitational wave production, or even in the kind of later universe, potentially the Higgs field could decay in this way as well. So there's lots of cosmological motivation for trying to understand this process in detail. So that's the picture as it stands, and people have been studying these bubble nucleation processes for a very long time, going back to work by Sidney Coleman and collaborators in the 1970s. This kind of standard paradigm has been using imaginary time methods, so Euclidean methods, to describe these bubble nucleation events. And these methods give really important insights, and they allow us to make detailed calculations of things like the rate of bubble nucleations. But they also leave a lot of really interesting open questions. In particular, conceptually, it's really difficult to understand from this Euclidean picture what I should expect this phase transition to look like in real time. What did the bubble nucleation events do in real time? And in particular, how do they interact with the real-time dynamics of the cosmological background? And also, with these Euclidean solutions, they're usually derived under quite stringent symmetry assumptions, which is fine for describing a single bubble. But if you have multiple bubbles, these symmetries are broken. And so the Euclidean approach is silent on the question of, should these bubbles cluster together or not, for example. So I'm showing you a little bit of a spoiler here, but this image was taken from a really nice paper that was led by Dalila Pirvu, who was a PhD student at the Perimeter Institute, Canada. She's now left to go and work in industry, but she found some really nice results from these lattice simulations studying, whether or not bubbles do tend to cluster together, and indeed it looks like they do. And in this paper, they found some really nice results about the kind of correlation function of these bubbles. So this is a really nice, tangible, qualitative effect, which was not captured in the existing Euclidean approach, but which shows us that there could be kind of new insights into bubble nucleation, which could also leave really important imprints on the kind of cosmological observables that I mentioned before. So the goal is to try to study bubble nucleation in real time and understand what that could mean for cosmology. And there are two methods to do this, which really work in tandem and kind of feed into each other. One is to use these real-time lattice simulations, of which I've already shown a couple of examples, and I'm going to come back to those in more detail towards the end of the talk. And the other is to build these analog experiments. So to get nature to solve the problem for us by building a system which has the same dynamics as the early universe field we want to study. So I'm now going to move on and tell you a bit about what those experiments look like and how we can try to build them in the lab. So one thing to emphasize first is that this isn't just a pipe dream. This is something which is actually happening right now. So we're working very closely with an experimental team led by Zoran Hadzababic at the Cavendish Laboratory in Cambridge. And they're building this early universe simulator right now. So I think something that's really cool about this is, this is relying on pre-existing experimental know-how. So these guys have an incredible level of control over these quantum systems and are able to do amazing things. And they're using their existing techniques to study a new problem. So this is something that really is achievable with the current kind of state of the art in this field. And yeah, we're expecting to kind of have a finished experiment and to be able to start collecting data in the coming months. So this is something that I really want to encourage you to stay tuned for. So I'm going to, over the next few slides, I'm going to try to just kind of sketch out, roughly speaking, where this analogy comes from. How do I go from this very non-relativistic cold atom system to something that looks like an early universe theory? So, we basically, what this system is we have a bunch of atoms, we cool them down, and eventually they transition to a Bose-Einstein condensate. So this is a state in which basically all of the atoms are sitting in the lowest energy state, and it's well described by a many-body wave function. So they're essentially all in this one state described by this psi that looks very similar to the kind of single particle wave function we might be familiar with. The main difference is that because this state is kind of macroscopically occupied, there's, say hundreds of thousands of atoms in this state, we become sensitive to the fact that these atoms can interact with each other. So we describe it not with the Schrodinger equation, but with this nonlinear Schrodinger equation, which is also called the Gross-Pitievsky equation. So we add this term, G mod psi squared, which just describes two-body scattering interactions between the atoms. And this will be vitally important because I'm going to show in the next couple of slides how this leads to the relativistic behavior coming out. So the first kind of hint of something that looks relativistic comes from looking at the dispersion relationship to this field. So I take little fluctuations of different wavelengths and I quantize them and I look at what their energies are. So it turns out that, if I look on small enough scales, I just recover the Schrodinger equation. I get something that looks very non-relativistic. So the kind of hallmark of this is a quadratic dispersion relationship like this. But if I look on large enough scales, long enough wavelengths, I get a linear dispersion relationship. And this is really interesting because that is exactly what you would get for a relativistic scalar field, albeit one that's massless, so that doesn't have any potential. So it's not quite what we want, but it's still really interesting to see how that comes out of what was a very non-relativistic system. And so here, that proportionality between the mode frequency and the wave number is this speed of sound c. So you can think of these modes as like phonons, little sound waves in the system. But in our analogy, this speed of sound is going to behave in exactly the same way as the speed of light does in the early universe theory. So the next step is to go from having what looks like a massless relativistic field to having a massive one, so one with a potential. And the easiest way to do this is to, rather than having a single atomic condensate, a single cloud of atoms, we have two clouds of atoms and we couple them together. We get them to talk to each other. So concretely, you could imagine two different hyperfine states of the same atomic isotope. And if you shine a light on them with the right frequency, then you can transition between these two different states. So we get what's called a Rabi coupling. Now, it turns out if you study the relative phase between these two different clouds, this degree of freedom has a potential that looks like this. So it's a cosine potential. And it's really intuitive to understand where this comes from because if I put my two clouds out of phase with each other, well, they want to talk to each other and kind of equalize their phase. So there's an energy cost associated with that. So you're then sat at the top of this potential. And it wants to drop down into one of the true vacua, which corresponds to zero phase difference. But of course, because there's a 2 pi kind of ambiguity in the phase, we have a periodic kind of series of true vacua like this. Now that's all well and good, but that means that, that antiphase state sitting at the top of the cosine potential there isn't going to give us bubbles. It's just unstable. It just wants to decay immediately. So there's no kind of metastable behavior that we need to see this kind of first order transition. The way that we get that is by playing around with the coupling between the two clouds. And in particular, if you modulate this coupling very rapidly, it turns out that this is, in an effective kind of slowly evolving picture of the field. This looks as though you have a effective potential like this. So one in which there is now a barrier between this antiphase state and the in-phase state. So this now looks like we have a false vacuum in our potential. And to build some intuition for this, the kind of mathematics of how this drops out is exactly the same as for a classical pendulum. So a classical pendulum has a cosine potential. If I put it up like this, it wants to drop back down. But if I rapidly oscillate the pivot point of a pendulum, you can actually stabilize this upward position. And that's illustrated in this little GIF here. So this is kind of the same thing that's going on here in terms of the dynamics of this phase. So now we have a false vacuum potential. And if I go back to that dispersion relationship I showed before, we see that now in this relativistic regime on large scales compared to the kind of typical atomic scales of the system, we get something that looks exactly like the dispersion relationship of a massive Klein-Gordon field, where this mass is then set by the curvature around the false vacuum and that potential. This is exactly what we wanted to see. And in fact, I won't give all the details here, but this analogy goes much further than this. So it's not just talking about little fluctuations around the false vacuum. You can actually show in terms of fully non-perturbative deviations in the phase that the analogy holds and that this system really does behave like an early universe field in a false vacuum potential. So in the kind of final few minutes, I'm going to tell you about the theoretical work that me and my collaborators are doing to try and understand this analogy in more detail and to kind of prepare the way for the coming experimental data and, how are we going to extract cosmological insights from that data. So our main tool in doing this is these semiclassical lattice simulations. I've already shown a couple of results from these, but just to tell you a little bit more about how these simulations are done and what the approach is. In a sense, this is sort of the opposite of the Euclidean approach, in which you start with a classical state, if you like, just a uniform homogeneous state in which you kind of ignore the fluctuations in the field. And then your field takes a very non-classical path, an imaginary time, and you end up with a bubble. And this kind of trajectory is called an instanton. What we do in the lattice simulations is sort of the opposite. So we put the quantumness of the problem into the initial conditions by sampling from the spectrum of vacuum fluctuations. So we put those into the initial conditions, but we then just evolve forward in real time using the classical equations of motion. And you can show that to leading order in H bar, so semi-classically, this should be completely equivalent. So this is what's called the truncated Victor approximation. This is used routinely in atomic physics and quantum optics simulations, and is also the same kind of idea that underpins simulations of inflation and reheating in cosmology. So this was first applied to this problem of bubble nucleation in this really nice paper that was led by Jonathan Braden back in 2018. And it has opened up a really exciting new way of studying bubble nucleation numerically. So I'm going to show you a couple of simulation videos to show you the kind of current state of the art in this. So these are both two-dimensional lattice simulations. The one on the left is for the full analog system. So with these two different atomic species, the modulated coupling and everything. And on the right is just solving for a Klein-Gordon equation with a false vacuum potential. So you can see that there is clearly very similar kind of processes happening. We get these bubbles forming in the analog system and that expand then at the speed of light or the speed of sound in the atomic system. There are clearly some differences as well, and these are the kinds of things that we're still trying to unpack and understand at the moment in order to probe this analogy more deeply. But we have some ideas for where these could be coming from. So what are the kinds of observables that I can extract from these simulations? And in particular, with the idea of, being able to compare with experimental data at some point in the near future. Well, one thing you can do immediately to make contact with the Euclidean formalism is to extract decay rates. So I can carry out a large ensemble of these simulations. I can see that they all transition at different times from being mostly in the false vacuum. So this is a volume average of the value of this relative phase field. They go from mostly being in the false vacuum to at a certain point, they start transitioning and they go up into the true vacuum. And so I can count the times at which these transitions happen and produce a plot like this. So each of these curves is for an ensemble, an ensemble of simulations where I'm just counting how many of the members of this ensemble still survive. So how many instances of the field have not yet decayed. So from this, I can extract a decay probability per unit time. And I can check, does this change with the parameters of the system in the way that I would expect? And the answer is yes. So we get a really kind of non-trivial confirmation of the physics that we're interested in. There is an interesting issue that is still open, which is that the overall normalization of this decay rate is currently very different between the Euclidean prediction and what we get from the lattice simulations. And we have good reason to think that this is down to an issue of renormalization. So how do you account for differences between the bare potential you feed into the lattice simulations and the effective one that the modes actually feel? And so this is a really interesting ongoing line of investigation, which I think Emily will touch upon in her talk. So please check that out if you're interested. But to sort of wrap up, I want to point out that, something I think is really, really exciting about these simulations and about the analog experiments is that we can look at things that, we hadn't even thought about as observables before, and things which are really difficult to access in this kind of Euclidean picture. So again, I'm taking some figures from another paper that was led by Dalila Pirvu, who I mentioned before, showing that from these lattice simulations, you can extract all kinds of interesting observables. We can look at correlations between bubbles, like I mentioned before. We can look at peculiar velocities. So that was an interesting finding that the bubbles tend to form with, a distribution of velocities that can tell you about the underlying physical processes. But one that I think is particularly cool is precursor events to the bubble. So if you take many, many of these bubble nucleation events and you stack them, what you find is, yes, after the nucleation time, you have the kind of the bubble profile you would expect from your Euclidean calculations. But you also find that beforehand, there's this coherent oscillation. And you can track this backwards in time through the simulations and find you get this kind of breathing oscillon feature, which eventually gets kicked and evolves into a bubble. So I think this is a really, interesting kind of new way of thinking about bubble nucleation that we're excited to explore more. So to wrap up, I hope I've convinced you that vacuum decay is a really interesting process in cosmology, but is currently still not fully understood, and there are some interesting conceptual questions that we want to try to understand, which could have a real bearing on cosmological observations. I've told you about some cold atom analog experiments that will be able to give us the first empirical tests of vacuum decay. And these experiments really are being built right now. So I encourage you to stay tuned and listen out for future developments in this. Thank you very much for listening.